So time to go over the first exam. And let's just say up front that there were some people who did fantastically well, amazing. And then there were a few, well, maybe more than a few, who struggled a bit with this exam. And so we're going to talk about it. We're going to talk about some of the mistakes that people made, some of the struggles that they had. A lot of things fall into a few basic categories. There's the things like transcribing, forgetting minus signs, forgetting parentheses still work like parentheses do, copying errors, algebra errors. They were pretty rampant, and those errors add up because they tend to snowball. Small errors become medium errors, become big errors. So you want to be patient, slow down, and put in some time to make sure that you don't have those errors. Now, the other thing that happened, a lot more than I expected, was that people would take problems that were similar on, say, a practice exam or some other example done in class, and then they'd say, aha, I'm going to fit the question I'm working on to match that problem I had done, even if there was no connection other than a few key words. I think it's important that you need to develop a sense of like, okay, what is the tool that I need, and when do I know how to use it? And a lot of people, I think, know how to use the tools, they just don't know when. And you have to be careful. And so if you were one of those few who didn't do very well, you get another chance, because there is another test coming up at the end of the semester, the final test, you might say, and that's comprehensive, which means that some of the ideas that were on this test will come back. And so more to do, right? But let's get going. Let's work our way through the test. Now, of course, there's the front page. Not much to see here or to do. You'll notice each problem is worth the same number of points. So the total was 60, and it's true. Nobody got above 60 on this exam. They might say, did anybody get 60? Yes, we did get people who got 60. So it is possible to be a student and to do really well. Well, that shouldn't be too surprising, right? All right, here we go. Number 1, find an explicit solution to the following initial value problem. And we see there's a derivative here. dy dx is cosine squared of x times y squared, and y of pi squared equals a half. So this is a differential equation, and look at it, we can see right away, hopefully we can see that, hey, we can think of it as two things. This cosine root x over root x, and then there's this y squared. So in other words, it's some function of x times some function of y, which tells us that this is a separable differential equation. And so we're like, wow! So we know how to solve separable differential equations. It's one of our nice categories. So how do we go about doing it? Well, there's 3 steps. Separate, integrate, uncomplicate. All right, so we just have to follow those 3 steps, and life will be good. So the first step is the separation. So let's put all the y squareds over on the left. Well, we'll leave the dy. The y squared here will come across, so we can think of it as 1 over y squared, or since we're preparing ourselves to do calculus things, 1 over y squared in a more calculus-friendly way is y to the minus 2. So y to the minus 2 dy equals, and over here, we can, again, more calculus-friendly, cosine x to the 1/2, the square root of x downstairs, you think that's x to minus 1/2 dx. All right, so there we go. There's our separation. And now we need to do our integration. So we integrate both sides. Now the integral of y to the minus 2, well, that's not so bad because it's the right form where we just add 1 to our exponent, which would be y to the minus 1, and then don't forget to divide by that new exponent. So that becomes minus y to the minus 1, and that'll equal what? Well, this is probably the hardest part of this problem, is how do we do this integral? Because it's like a weird thing, because there's this function, x 1/2, inside this other function cosine. So how do we handle function inside of function? If only there was some sort of way for us to handle this. And, well, there is, right? Function inside of function, if we were talking derivatives, we'd say chain rule. When we talk integration, that's substitution. So, oh yeah, that's right. Substitution works here. Okay, so what does that tell us? Well, we would say let u equal x to the 1/2 power, because that's the inside function, right? So when you're thinking about substitution, look for the function on the inside. Then what do we have? Well, du would be 1/2, and because the 1/2 comes down, x to the minus 1/2 dx. And we're like, what? X to the minus 1/2 dx? X minus 1/2 dx? Matching. Ha ha ha. So that means that if we make this u, then this part right here, well, it's not quite du, because we're not having a half here, but you can imagine multiplying through it by 2, so that becomes 2 du. All right, well, what's the integral of cosine of u times 2 du? Well, the integral of cosine is positive sine. So that becomes 2 sine of u, and of course, plus some constant, which we'll handle in just a moment here. And, oh, don't forget, u is x to 1/2. So that says that the integral of the right-hand side is 2 sine squared of x plus some constant c. All right, so let's update. So we have minus y to the minus 1 is equal to 2 times sine of square root of x plus some constant c. All right, now are we done? Well, no, there's an initial value. So we need to work with our initial value now. And that's part of our uncomplicate strategy. So let's now plug in our initial value. So what we have is we're told y of pi squared is equal to 1/2. So that means when we plug in x equals pi squared, we should get out y equals 1/2. Now, y to the minus 1, what is that? We probably should have written it over here. That's the same as really minus 1 over y. And so if we talk about 1/2 to the minus 1, that becomes 1/2 to minus 1 is 2. And don't forget the minus sign. So we have that minus 2 is equal to 2 sine square root of pi squared is pi, then plus some constant c. But, hey, what do you know? Sine of pi is 0, so that part goes away, and so we can make the conclusion c is negative 2. All right, so updating, we have that minus 1 over y is equal to 2 sine square root of x minus 2. Well, move the negative across. 1 over y is equal to 2 minus 2 sine of square root of x. And finally, if we want to solve for y, well, flip both sides. And so we get our final answer, y is equal to 1 over 2 minus 2 sine square root of x. And there we go. That's it. There's our answer. So where could we make mistakes here? Now, a big mistake at the beginning would be to say, hey, I don't know what kind of differential equation is, so try to do something that doesn't apply. Maybe we are like, oh, hey, maybe this is some kind of first order. No, it's not. Or maybe there's some kind of weird substitution or Bernoulli or something complicated. But no, it's separable. And it's important to recognize what type of problem you're working on. If you don't know the type of problem you're working on, you're not going to make a lot of progress. But I would say that probably the hardest thing about this problem is the integration here. Because you have to say, oh, hey, this is a little bit subtle, but it's not so bad. We see that it's sort of a weird situation where we have a strange function inside of a function. We're like, yeah, there's rules for that. We know calculus. It's not so bad. And so once we get past that integration, then nothing's too bad. What a nice way to start the exam. You should always start the exam with a fun problem. And of course, ideally, they're all fun problems all the way through. So on to the second problem. Find a general solution of something. x e to the xy plus 2xy plus 1 over y. All of that is multiplied by dy dx plus y e to the xy plus y squared plus 10. And put it all together, you get 0. And of course it says you may leave your answer in an implicit form, which is probably not too surprising given that it gives us the question in a very much implicit form. See how we have y inside of the exponential and outside? That says you're going to be hard-pressed to actually find something that's explicit. Now look at this, we have to start saying, well, what can we do? Well, because there's no way to get the y simultaneously outside of the exponential and still keep these other pieces outside of some other strange exotic function, there's not a lot of options here. It's not going to be separable, kind of hopeless there. It's not going to be linear first order. But in some sense, the hopelessness actually sends a signal, says, when we look at these pieces, and there's two pieces here. There's the piece attached to the derivative, and then there's this other piece that's not attached to the derivative. We say there's some sort of similarity going on here. Namely, they both have things that look very close to each other, this e to the xy. Now, why is that sending a signal? Well, that sends a signal that this might come from something exact. Because in exact, you often have pieces that say, oh, I'm taking derivative of the same function just with respect to different variables. And so the pieces will end up looking very similar. So the fact that we have these similar looking pieces, that's like, wow, we're thinking maybe exact. Okay, so let's rewrite this just a little tiny bit to help us put us more in that mindset. So right now we're thinking, is this exact? And we'll have a question mark here. And we'll answer that question as we go through. Spoiler alert, yes. But we don't know right now. Okay, so how would we write this? Well, for me, the best way to write this has x e to the xy plus 2xy plus 1 over y dy plus y e to the xy plus y squared plus 10 dx equals 0. So in other words, imagine that dy over dx was actually two things, a dy upstairs, a dx downstairs, and you multiply through by dx. And the reason I like to do it this way is it really helps to say, hey, what is what? So if we think it's exact, then we would say the thing that's in front of the dy, this part right here, would be the derivative of what we want with respect to y. And what's in front of the dx, that would be the derivative of what we want with respect to x. Okay, so we say, well, what can we say about our function f? Well, f, we integrate. We can do it in any order, so let's suppose we do it the first with the derivative with respect to y. So partial f partial y dy. Okay, so that's the integral x e to the xy plus 2xy plus 1 over y dy. And now we start working through it. And here, there's some parts that will be a little bit subtle, but not too bad. Okay, so let's tackle probably one of the hardest parts here. How do we handle this piece? Now we're integrating with respect to y, so x is a constant. So think of it like 2e to the 2y, 5e to the 5y, something like that. Well, the x in front, that's okay. When we integrated e to the xy, well, if you integrate e to a constant y, it's e to that constant y divided by that constant, because you got to do some compensation here. So what happens is the integral of x e to the xy, well, the x comes along, and then it'll be e to the xy divided by x, which means that the x's cancel. So what we really have is this becomes e to the xy. So that's that part. That's the hardest part to integrate. All right, integral of 2xy, and we're integrating with respect to y. So we treat x like a constant, integral of 2y, y squared. So plus xy squared. Integral of 1 over y, well, natural log of y. Now, if you're a real stickler, you could be, well, natural log of absolute value of y. I'm not going to be that much of a stickler. Okay, anything else? Plus c. But what kind of plus c? It's a constant with respect to integrating with respect to y, and so we have to say some function which depends on x. Okay, so if it is exact, and it would mean that our function that we're after to help us get our answer looks like this. Okay. Well, by the same idea, because look, f is the integral partial f partial x dx. So we're going to integrate this part with respect to x. So that's y e to the xy plus y squared plus 10 dx. Well, the first part, we've already had that discussion. Only thing that's changed is our roles of x and y, but the ideas haven't changed. So this will again be e to the xy. Here we're integrating with respect to x, so y squared is a constant. If I integrate a constant with respect to x, that's a constant times x. Or we could write it as x y squared. Integral of 10 with respect to x is 10x. And then, of course, some function of just y. Now, so far, everything we've done, we can always do whether it's exact or not. We haven't yet answered the question, is it exact? Now, we could have, before we started, answered it by taking derivatives, right? If we take the derivative of this part with respect to x and compare it to the derivative of that part with respect to y, and if they matched up, we'd be done. There's this other idea, and it's one that I kind of like, which says, hey, on our road to finding the answer, if we think things are exact, we look at the pieces from these two integrals, which involve both variables, and namely those two things. And here's the rule. If these match, in other words, things that involve both x and y, as long as those match, then you have an exact function. And so since these parts with both x and y match, we can say the function, well, or if you like, the problem is exact. So now we can come up here, and is it exact? The answer is yes. All right. Well, how does that help us? Well, the way it helps us is we can now say, okay, to finish, we put everything together. So what does that mean? Well, what we do is we come here and say, what does our function f of x, y look like? Well, we look at the parts that matched, that have both things involving x and y. We need to have those. So we have e to the xy plus xy squared. And now we say, okay, we need the things that just involve one variable. So there's a log y, so that's part of our answer. So plus log y. And then here, there's a 10x, and that's part of our answer. And there we go. There's our desired function. Now, that's not our answer because we're looking for a solution to the differential equation. To get our answer, we set our function equal to some arbitrary constant, which here I'll use capital C. It's not this constant function of x, it's some arbitrary constant c. And there we go. That is our solution. Now, what's bad here? Now, again, this is one that's mostly just a matter of, can you recognize the type of problem this is? In some sense, it's a little bit easy to spot exact because you have things that are like, oh, this looks kind of hopeless. And you're like, hopeless? Exact. Exact is about the only place where we see hopeless things showing up that we have a chance at. And so that's one of the signals. I think the other hard part is being able to nail down that integral and make sure we get that right. And of course, don't forget the c over here. That can be a simple mistake. And we don't want simple mistakes. We don't want any mistakes, really. But, all right. Number 3. During a zombie apocalypse, the number, P of t, of thousands of people infected after T weeks satisfies the logistic differential equation. And so there it is, yep. assume that in an isolated city with a population of 40,000, and so here they're being very clear, so m equals 4, which means that we're thinking of, we have this city that we're having people become infected, and how many people can get infected? Well, up to everyone. So when we think about m, that's the carrying capacity. So we say, okay, so that makes sense in terms of the problem. All right, 1/4 of the population is infected at t equals 0. And 1/2 is infected after 1 week. And how many weeks will 3/4 of the city get infected? Okay, so let's parse a couple of things. So what do we have? Well, we are told p prime is equal to k, p, and then we have 40 minus p. So we're using the fact that m equals 40 here. And we have some information about what's happening with our population. So we're told our population at time 0, well, that's 1/4. Now, how much does 1/4 correspond to? It's 10,000, but we're measuring in thousands, so that says our population at time 0 is 10. Our population at time 1 week, well, that's 1/2. So that would be 20. Okay, so that's our information. We have our differential equation, and we have some information, some initial value, what happens after 1 week. And now the question, what can we say is the time when we get to 3/4? So we want to know really a time. So in other words, what's this input? So at what time do we get to 30? Okay. Well, Now, there's some nice things. There's a reminder here. It says remainder, but it meant to say reminder. The solution of the logistic ODE, and that is the logistic ODE, is this expression. So we're like, hey, beautiful. Let's use that. And so let's write it down. So we have that our population at any given time t, well, we're going to take m, which is 40, times p0, which is 10. So we have 40 times 10. Divide that by p0. Well, what is p0? That's 10 plus m minus p0. So that's 40 minus 10. So that would be, well, I'll just write 40 minus 10. We'll clean it up in a second here. And then we have e to the minus k, which is something we don't know. That's probably something we have to find. But we do know m. M is 40. So we have 40 kt. Now, one thing we can do is all these numbers are divisible by 10. So we can rewrite this as 40 divided by 1 plus 3 e to the minus 40 kt. All right. Now, what do we want? Well, what we want to do is set the population to 30 and solve for t. But we can't solve for just t because we don't know k. So we need to know k. So how do we use it? Well, what haven't we used so far? Well, we haven't used this information, namely what's happening after 1 week. So let's use it. Okay, so we can say here is that 20, that's equal to what happens at 1 week. Well, that's the same as 40. Divide that by 1 plus 3 e to the minus 40 kt. Well, we can move this across and divide by 20. So that tells us that 1 plus 3 e to the minus 40k times t needs to equal 2. Okay. All right. Well, that's not bad. That's like useful information. So we can even start doing some other things. So notice, what can we do? Oh, whoops. Ha! I put t here. What should I have put? 1, because we're plugging in time equals 1. See? You got to pay attention. Otherwise, you'll make mistakes. So that's really a 1. All right. So, see, that's what I mean by transcription errors. You can make small transcription errors if you're not paying attention. All right. So what will we do? We can subtract 1 divided by 3. So we can say, look, e to the minus 40k is equal to 1/3. And now we can take the natural log and we can say, minus 40k equals the natural log of 1/3. But if you know properties of natural log of 1/3 is the same as minus natural log 3. And therefore, we have that k is 1/40 natural log of 3. All right, great. Now we know what k is. So what do? Well, we're ready. We know everything. We just need to solve for our time. So let's come down here. I'll move this up a little bit. Okay. So we have that 30. That's our population at some time, and we want to solve for that time t. Okay, that's equal to our 40 divided by 1 plus 3. And now, well, let's actually look at this. Minus 40 times k. Well, minus 40 times k is the same as minus log 3. We didn't even really need to simplify here. So it'd be e to the minus log 3 times t. Okay. Well, we'll run through a similar process, right? We can multiply over, divide, so we can see that 1 plus 3 e to the minus natural log of 3 times t is equal to 40 over 30, which is 4/3. Subtract 1. That'll make it 1/3. Then divide by 3, and we have e to the minus natural log 3 times t is equal to 1. What did I say? Subtract 1 to get 1/3, and then divide by 3, you get 1/9. All right. Now take natural logs, and we can see that minus natural log of 3 times t is natural log of 1/9. Well, that's the same as minus natural log of 9. But now, here comes the fun thing. What is 9? Does it look anything like 3? It does, right? It's 3 squared. So this is minus natural log of 3 squared, which is minus 2 log 3. And then we're like, what? Minus log of 3 times t needs to be minus 2 times log 3. So divide both sides by minus log 3, and we come to the conclusion that t equals 2. So the answer is 2 weeks. Actually, kind of almost too nice, right? At 0 weeks, we're at 10. At 1 week, we're at 20. At 2 weeks, we're at 30. You're probably thinking, hey, at 3 weeks, we'll be at 40. No, we can't, because we can never get to our carrying capacity. It just happens to work out really nicely in this case. Almost as if somebody had planned it that way, right? Well, maybe. So there you go. And so that's actually kind of a fun problem. In some sense, this is a kind of problem that doesn't really involve much differential equations, because notice we never really solved any differential equations because it gave us the formula for it. So at the end of the day, mostly this is just a matter of really two things. One is, do we know our college algebra? In other words, can we move things around? Can we take things out of log? And hopefully we do. At this point, hopefully we do. The other thing that we need to know a little bit about, and probably was one of the more challenging things, was interpreting, because we had sort of two senses of population going on here. And so if you confuse the two, it'd be easy to make a mistake and hard to get going. So what are the two senses of population? Well, namely, we had one sense of population, which was the population of the city, and the other sense was that we had the population of the infected. And so if you mix the two up, yeah, that would basically ruin the problem, and you wouldn't be able to get anywhere. So how do you know which is which? Well, the answer is be careful. Now, that's not a very convincing answer, but it's an honest answer, and it is an accurate one as well. And so when we say things like be careful, well, we mean things such as, all right, when you are told what is P of T, well, the problem, it tells us P of T is people infected. And so we say, okay, P of T, that's the number of people infected. So when we see that the city is a population of 40,000, we say, well, wait a second, that's just how many people are in the city. That's not the number of people infected. So this data point is not about P of T, it's about something else. And then they say, yeah, well, it's about M. It tells us how many people could get infected. So that, I think, was probably one of the hard parts about this problem. All right, 3 problems down. That means we're halfway through. Doing great, right? I hope. Okay, number 4. Find all critical points for the ODE. So we have this dy dt equals 3y squared minus y cubed. And then, of course, after we've found them, it says determine whether each critical point is stable, unstable, or semi-stable. Sketch the phase diagram. And then it says, suppose we're told that y of minus 2 equals 1. What happens to y as time goes to infinity? All right. So, here's the nice thing about this. Notice what it's not being asked. It doesn't say solve the ODE. And we're not going to, because this is one that would take a long time. And even after we solved it, it's one that we couldn't get into a nice form. Now, that's not so obvious from the start. And I'm asking you to trust me on that, because we definitely don't want to go down that road. So, okay, so it doesn't have a nice form. We're just going to have to go and do something else. So what do we do? Well, we think back and say, okay, this, for example, says critical points. And so in particular, when we're in the case we have y prime equals f of y, that really corresponds to when does f of y equal 0. So we say, all right, so to find the critical points, that's not so bad. So we have that 3y squared minus y cubed needs to equal 0. Well, notice we can factor out y squared. 3 minus y equals 0. And now we see, aha, y equals 0 or y equals 3. So these are the critical points. All right, so that's the first part. We found them all. And then it says determine whether each point is stable, unstable, or semi-stable, and sketch the phase diagram. We'll actually reverse the order of that. Let's sketch the phase diagram, and then we'll talk about stable, unstable, or semi-stable. So to sketch the phase diagram, well, we draw a line, and then we can mark our points. We have 2 of them, 0, 3, all right, success. Now what we need to do is we need to look at the question, what can we say about y prime in each one of these parts? Well, all right, how do we do that? Well, we just put in numbers. So suppose we put in negative 1. Well, we can do it here, right? Negative 1 squared is 1. 3 minus negative 1 is 4. Everything's positive. So we see, aha, y prime is positive. Okay, how about something like positive 1? Well, we get 1. And 3 minus 1 is 2. Still positive. All right, how about something bigger than 3? 4. 10, doesn't matter, just pick something bigger than 3. So 4 squared, 16. 3 minus 4, minus 1, negative. So y prime here is negative. Now, once we know the signs, it opens up our eyes, right? As the saying goes, we saw the sign, and it opened up our eyes. We saw the sign. So where y prime is positive, that says y is moving up. And when we have this phase diagram, that means to the right. And so we move up from below 0. We also move up from 0 to 3. And when we're above 3, y prime being negative means we move to the left, which means we go in that direction. All right, so this part right here, this is our phase diagram. Okay, now we're ready to talk about stability. Are we stable, unstable, semi-stable? Well, 3 is pretty easy. We can see it, right? We're coming in, doom, 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 doom. And so that says we, if you're nearby, you move closer. So that's a sign of stability. Things like to head towards you. On the other hand, when we look at 0, things are doing this, right? They're sort of moving in unison, going up, up. Where it says below 0, we head to 0. Above 0, we go away. So that's semi-stable. So we can say, look, 3 is going to be stable, and 0 is semi-stable. Or semi-stable you can think of as being half stable. So we're stable on one side. All right, so we found the critical points, we did the phase diagram, and we've sketched. Are we done? There's one more thing. We have to find out, if y of minus 2 equals 1, what is the limit as t goes to infinity of y of t? And there's actually 2 ways to answer this question. Okay, so the limit as t goes to infinity of y of t, we can do it by use of the phase diagram. And here's how you do it if you have the phase diagram. So we have 0, 3, and we can, again, I'm just going to replicate the phase diagram. Now we say, what's our initial condition? Our initial condition says y at minus 2 equals 1. Now, what do we care about, the minus 2 or the 1? That's an important question. And the answer is we care about the 1. Because when we think about these functions, they're autonomous, which means we really don't care about the inputs. They're not input sensitive. It's the outputs that are determining behavior. So we're saying we start at y equals 1, which means we start here. So there's 1. Now the question is, where do we go? Follow the arrow. What does the arrow tell us to do? The arrow says, go up. Till when? Go up until 3. So from the phase diagram, we get that the limit is 3. All right, now, there is a second way to answer this question, and let's talk about that. What we can do is we can start with our phase diagram. Sure, if we think about our phase diagram, we should actually make a note here. So in our phase diagram, this axis here is y. And now we're going to swap and go into a two-dimensional diagram where we have x and y. And now what we're going to draw is we're going to draw solutions. So we know x equals 0, that's the solution. And we know x equals 3, that's the solution. And now we say, look, if we're below 0, we move up. So things are tending to do something like that. If we're between 0 and 3, we move up. So we tend to be doing something a bit like that. If we're above 3, we move down. So we are doing something like that. Now, what's our initial condition? Our initial condition, we took it off our screen here. Let's pull it back down for a second. Y of minus 2 equals 1. So that would correspond to saying we're at x equals negative 2, y equals positive 1, which is we're here. That's where we start. And then we say, well, what does the curve do? The curve moves something like that. And so, in the long run, we move to 3. So you can use either the phase diagram or say, hey, here's what these curves look like, and use that information combined to answer the question about the limit. All right, that's number 4. Now, what are some things that people did that probably they shouldn't have done? I would probably say one of the big things that I heard about people doing was they actually tried to solve the differential equation. And I understand it. It's like, hey, I'm taking this class. It's called differential equations. I learned how to solve some of these things. And I like partial fractions. I love partial fractions. I'm going to go crazy with partial fractions. But don't do more than what the problem asks you to do. I think that's one of the big challenges, is saying, hey, what is this problem asking me to do? And just realizing that's all you do. Don't do more. Don't do less. Find that, it's like Papa Bear and Mama Bear and Baby Bear. Be the baby bear. Just right. That's the amount you want to do. Just the right amount. And of course, the question, what is the right amount? Well, that comes a little bit with practice. And we'll get there. Hopefully sooner than later. All right, here we go. Number 5. Consider the differential equation 2x plus 1y double prime minus 2y prime minus 2x plus 3y equals 0. All right, differential equation. Great. And now what do we need to show? Well, okay, show that x, e to the x, and e to the minus x are both solutions for the differential equation. Now, I will say I actually spent some time grading on this problem. And some people had this sort of strange idea that says, I'll solve this differential equation. And of course, once I've solved it, then because I'll see, hey, these are the solutions, then I've succeeded. And there's 2 challenges to that. One, we don't know how to solve these because you'll notice these are not constant coefficients. The coefficients involve x, so we don't have the technology. So we can't do it. So that's a pretty big obstacle. Now, the other thing is, even if we could do it, that sounds like it might take a long time because it would take a long time. And we're not looking to try to burn ourselves with things that take a long time. So what do we do? Well, the answer is we just work through things and we say, what does it mean to verify? You might say, it doesn't say the word verify, it says the word show. Well, this is when we pull out our, knowledge that some words mean the same thing as other words. So show and verify are the same idea. So you show something as a solution by verifying it's a solution. Okay, so let's start with, doesn't matter, we have to do both of them. So let's start with x e to the x. All right, so how are we going to verify that x e to the x is a solution? Well, what we'll do is we're going to take 2x plus 1, and we'll take the second derivative of x e to the x minus 2, the first derivative of x e to the x, and then minus 2x plus 3 times the function x e to the x. All right, so in other words, we're plugging x e to the x in. And then we're going to see, do we get 0? And if we do, solution. And if we don't, check your work again. Because it has to be, because we're told that it's a solution. Now, some people ran it through and they said, it's not a solution. No, it is. You made a mistake. We're told it's a solution. It has to work. All right. Well, okay. So we keep going, right? Okay, so that's 2x plus 1. And now we come to, I think, one of the biggest challenges on this problem, which is how do you take these derivatives? Yes. And I think if you could get past taking these derivatives, you probably were going to make it. All right, so you have the function x e to the x. What's the right rule for taking the derivative of the product of x and e to the x? Yes. What rule do we need when we're taking the derivative of a product of 2 functions? It's the product rule. Okay, so the derivative of x e to the x, derivative of the first would be 1 times the second, so that's e to the x, plus x times the derivative of the second, so that's plus x e to the x. Now that's the first derivative. Now the second derivative, how do we do that? Well, actually, it's not so hard, right? Because it's the derivative of x e to the x, which we know, and then plus the derivative of e to the x, which is e to the x. So the end result is it's essentially the same as what we had here. There's just another e to the x. So we could say it's 2 e to the x plus x e to the x. All right. So now we brace ourselves and do the multiplication. So we do FOILing. 2x times 2 e to the x will give us 4x e to the x. And then 2x times x e to the x will be 2x squared e to the x. Then 1 times 2 e to the x, 2 e to the x. 1 times x e to the x will be, x e to the x. Now multiply the 2 through. Minus 2 e to the x minus 2x e to the x. And here, okay, multiply the x e to the x through. And of course, minus 2x squared e to the x and minus 3x e to the x. Notice, of course, the parentheses, the minus went through. A lot of people were losing minus signs left and right because they forget, oh yeah, minus signs do distribute through parentheses. It's still true. It's still true. All right. Well, now let's look at things. So let's look at things here. So let's look at anything that has a 4x or e to the x. Well, let's just say x e to the x. There's an x e to the x there. There's an x e to the x there. And there's an x e to the x there. And x e to the x there. So when we put those together, what do we see? 4 and 1 makes 5. Minus 2 and minus 3, that's not minus 5. And we put it all together, that cancels. Okay, so those cancel. All right, now what? Well, let's, next term, x squared e to the x. So there's an x squared e to the x. And there's an x squared e to the x. And that's the only ones. Okay, what do we see there? Cancel. Wow. Nice. Okay, how about just plain e to the x? Well, there's a 2 e to the x, and then there's a minus 2 e to the x. And so when we put those together, we say, hey, again, they cancel. So cancel, cancel, cancel. Everything cancels out. So what do we get? We get that it all becomes 0, which means it works. All right, we've plugged in x e to the x into the left-hand side. We got the right-hand side out. We have a solution. Life is good. Life is wonderful. Okay, now that was the hard one to check. But we still have to check the other one. Okay, so here we go. The other one is e to the negative x. So for e to negative x, we're going to do something very similar. Namely, we just run it through. So we have 2x plus 1, e to the negative x, second derivative, minus 2, e to the negative x, first derivative, minus 2x plus 3, times just the function, e to the negative x. Well, now, this is when we don't have to think too hard about the derivatives. When I take the derivative of e to the negative x, what happens? Well, it's e to the negative x with a minus coming down. And it comes down because, by the chain rule. Here, the e to the negative x, when I take the second derivative, a minus comes down, another minus comes down, which means that at the end, it's back to e to the negative x. So we have 2x plus 1 times e to the negative x minus 2 times minus e to the minus x minus 2x plus 3 times e to the negative x. All right, distribute, and we'll have 2x e to the minus x plus e to the minus x minus minus makes plus 2 e to the minus x. And here we'll have minus 2x e to the minus x and minus 3 e to the minus x. Okay, so let's just do our same process we just did. So we look at the x pieces here. There's a 2x e to the minus x, a minus 2x e to the minus x, and those terms will cancel out. Nice. Okay, and we have to look at just things that look like e to the negative x. So we have an e to the negative x, a 2e to the negative x, and a minus 3e to the negative x. And if we compare those, we see, aha, 1 and 2 makes 3. Subtract 3 makes 0. They all cancel out as well. So we get 0, and we're done. Finished. Great. So now we're done with part A. That's the verification. In some sense, this is kind of a little of the more intensive part of the computations on the exam. On the other hand, it's just more, you just follow your nose. And we know if we didn't get 0 out, well, we could do one of two things. We could either bluff and hope that the grader didn't check too closely, which may have helped a few people, but I think the graders checked pretty closely. Or we could say, oh, let me go back and check my work and catch some errors. They might say, hey, I got 0 out, but I lost points. Well, sometimes if you take the derivatives in the wrong way, things work out too nicely. And just because things work out nicely with the wrong derivatives doesn't mean that you found a solution. It just means, oops, you had a couple of errors and you just happened to get lucky. And, you know, we don't want our bridges to be held up by luck. We like it to be held up by engineering, right? That's the goal. It's a good goal. Good goal. Okay, now this is a problem with multiple parts. So on to part B. Okay. Use the Wronskian to check if the functions are linearly independent. And if yes, write a general solution for the differential equation. Okay, so we look at this and say, aha, we're going to do something with the Wronskian. So what is that? Well, that's when we have to do a determinant of a little matrix. So we would say the Wronskian of our functions, x, e to the x, and e to the negative x. And by the way, it doesn't matter which order you put these in. So, but pretty much everybody did it the same way. It's given like x, e to the x, e to the negative x. Well, that's two functions, so we're going to have a 2 by 2 matrix. In the first row, it's just the functions as given. X, e to the x, e to the negative x. The second row are the derivatives. And we don't actually have to work hard because we can read them off from up here. There's the first derivative, and there's the first derivative. So we can say, okay, that's e to the x plus x e to the x. Here it's minus e to the minus x. Okay. Now, there were a few answers that didn't have a 2 by 2. And I will say that really was kind of unusual. I gotta say in general, there were some problems on this exam that were so creative. It's like, wow, you know, don't tell us that engineers can't be creative, because they were coming up with the most unusual solutions. It's like, what were you thinking? That's not how numbers work. That's not how adding works. But here are some of the things that happened where there would be people who would have 2 columns but 3 rows. And Wronskian should be square. And so however many columns you have, however many functions you have, that's how many rows you should have. So if you have 2 functions, you should only have 2 rows. If you have 3 functions, you should have 3 rows. The other thing that happened, and I suppose this is the danger of practice exams, is there was a practice exam which used 3 functions, and one of them was called y. And so people started doing that. But that's not related to this problem. So this is a case of some people trying to overfit. And they were like, hey, I worked hard to do that problem on the practice exam, and I worked hard to remember it. So I'm going to put it here, regardless of whether or not it belongs. And so be careful. Don't just put things just because they remind you of like, oh, once upon a time I heard this wonderful story about a problem. No, put problems if they relate. So you have to be careful here. And I apologize if I'm coming across as being aggressive. I want you to do well. We really want you to do well because it makes grading so much better. And we want grading to be better. All right, back to this problem. Now, another thing that was happening was that people were forgetting how do you take these little 2 by 2 determinants. So the rule is that we're going to multiply the functions on diagonal. So we're going to go downhill, and we're going to go up. And the other thing to remember is that we add the one going down, we subtract the one going up. So here we go. We're going to take x times e to the x, and we're going to multiply it by minus e to the minus x. So we have x e to the x times minus e to the minus x. Subtract. Well, here we'll have e to the x plus x e to the x multiplied by e to the minus x. Now, some other fun things that we're showing up a lot. What happens when you multiply e to the x times e to the negative x? What do you get? You don't get e to the negative x squared. You get e to the 0. You add the exponents. So x plus negative x is 0. E to the 0, also known as 1. So the first term, we're going to get x with a minus sign. Well, that's also known as minus x. And subtract, well, we can pull out e to the x here, multiplied by e to the minus x. Again, that'll be a 1. So we pull out the e to the x, we're left with 1 plus x. So that is the same as minus 2x minus 1. Now, what's the important thing? When we're asking the question about the Wronskian, the question is this 0? Not is this ever 0? Is this the 0 function? And we say, look, this is not the 0 function. But it is true that it does equal 0 at a point. And it equals 0 when 2x plus 1 equals 0. And we would say, yeah, but we expect it to equal 0 when 2x plus 1 equals 0, because that would be a problem in our differential equation. So if you ever have something vanishing, is what I should say, then yeah, you should expect something to happen with the Wronskian at the point where that part vanishes. Okay, but the point is this is not a 0 function. Since it's not a 0 function, by the Wronskian, that says these functions are linearly independent. And of course, the very slow part here is spelling things out like linearly independent. Now, since they are linearly independent, we need to write a general solution for the differential equation. So, we need to figure out what do the solutions look like for this differential equation. Now, we know it's a second order. We also know it's homogeneous and linear. So that says if we could find two linearly independent solutions, we can apply superposition. Well, we have two solutions. We know that they're linearly independent, and so are great. Oh! We don't have to do any work. We can just take everything that we've already done in this problem and just put it all together and say, okay, so by superposition, you don't even need to say this, but we'll go ahead and say it here. We can say that our general solution, general solution is you take some constant times your first function, x e to the x, plus some other constant, e to the minus x. And we're done. That's it. That's the answer. Now, I will say there was something interesting that people did. I mean, there were some things that were not interesting that, made us like, oh, what was the thinking process there? But some people said, hey, since x e to the x is a solution, shouldn't e to the x also be a solution? Now, that's actually not a bad thought to have in general, but where is that thought coming from? So that thought comes from when we talked about linear, homogeneous, constant coefficient differential equations. We said, hey, our solutions look like this. And so if we have x e to the x, in that setting, we'd have to have e to the x. Now, are we in that setting? No. No, these are not constant coefficients. The 2x plus 1 and 2x plus 3 depend on x. And therefore, it is possible to have x e to the x be a solution, but e to the x is not. So, all right. Well, that's number 5, which means we're almost there. Just number 6 to go, and then we're done. All right, number 6. Consider the following initial value problem for a spring mass-dashpot system. So if you prefer, you could just call it a spring mass system. You could call it a spring mass damper system. So we have x double prime plus 4x prime plus 29x equals 0. And there's initial conditions. X of 0 equals 2. X prime of 0 equals 1. So find the position function, x of t, and circle the type of damping that occurs. All right. Well, let's think about it. Really, it's saying find the position function means solve the differential equation. Okay, so this is back. You know, we solved the differential equation number 1. We solved the differential equation number 2. And then we had a dry spell. 3, 4, and 5 do not have a solved differential equations. So finally, finish up, we're like, okay, you know, let's solve one more differential equation, you know, for old time's sake. So, all right, let's see, what can we say? Well, we have our x double prime plus 4x prime plus 29x equals 0. Now, a constant coefficient, linear, homogeneous. So we say, okay, look, r squared plus 4r plus 29 equals 0. And now we need to solve. Well, you can do a couple of ways. You can do completing the square, works pretty well, or you can do quadratic formula. A lot of people opted for quadratic formula, so we'll do that too. So we would have r equals negative b, so that's minus 4 plus or minus the square root b squared, which is 16, minus 4 times a times c. So 4 times 29. All that over 2a. So that'd be 2. All right, now one of the most complicated computations on this exam. What's inside that square root? Okay, well, let's do a little bit of math here on the side. So 4 times 29. Well, that we can think of as 4 times 30 almost, right? Which is 4 times 30 is 120. But we went over by how much? We went over by 1 copy of 4. So subtract 4 off, that's 116. Now, if that doesn't sound like a legitimate thing to do, think of it as 4 times 20, which is 80, and 4 times 9, which is 36. 80 plus 36 is 116. So 16 subtract 116 is minus 100. Okay, so inside the square root is minus 100. That was probably one of the hardest computations we did. 4 times 29, a 2-digit number. I should point out that you should start to get a feel for like, hey, how big is this number? So 4 times 29 is really close to 4 times 30. So you should say that should be really close to 120. So if you're not close to 120, you know you made a mistake. And so you should try to catch yourself. And that's one of the reasons why we want you to develop a number sense. Yeah, we get it. You're going to have calculators out there. But you still have to be able to think about things. You're still going to think about things even without ever punching things into calculators. And so you need to have that number sense that says, oh yeah, this seems reasonable, or oh no, that doesn't seem reasonable at all. We should really delve deeper into these computations. So, okay, back to our problem. So here's something that happened to a lot of people. They forgot the minus. All right, well, we won't do that. We won't make that mistake. And, okay, so that's minus 4 plus or minus the square root of 100 is 10. And because of the minus sign, 10i over 2. Now, here's a mistake that I saw way too often, which is, this is negative 2. People got that. Plus or minus, and then people would say 10i. why is that a problem? Well, they say, look, 2 goes into -4, that's -2. Then you have the 10i. But 2 also goes into that, so it's -2 plus minus 5i. By the way, at this point, if you remember the rules, we can actually answer the type of damping that's going on. We see complex roots, and there's some real part here that's not 0. So that corresponds to underdamping. We'll come back and talk about that again later on, but we'll go ahead and circle that because we're like, hey, we want the points. We're not going to forget to do that. Might as well do it soon because we have to do it at some point, right? So why not do it soon and get it done with? Now, we're not done with the problem, but what we've done is we said, hey, we know our roots to that polynomial. Now, the reason that that's good is because we can now say, all right, well, that means that our function that we want, our x of t, looks like some constant e, and this part up here is what goes with the exponential part, so minus 2t and cosine 5t plus some other constant, e to the minus 2t sine of 5t. So this is how we handle complex roots. It becomes combinations of the exponentials and the cosine sign. So it's important to remember that, because if you try to redrive everything on the fly, it can throw you off. Now, another thing that I should point out, and it's a mistake I sometimes make, and because I make a mistake sometimes, I really try to check myself on things like this, where I'm like, I know I'm susceptible. We should have this be a function of t. Now you might say, well, how do you know it's supposed to be a function of t? Well, because it actually tells us right here. Do you see how it says x of t? It says our answer should be a function of t. And so if you write it down and you have x's here, oops, that means you have the wrong variable. And yeah, the grader looked for that. So, we don't want to make any mistakes. Well, we don't want to make too many. All right, now are we done? No. Why not? Well, because we haven't solved the initial value. By the way, now that we see it in this form, we can see again, aha, this is underdamping because we still have oscillations. That's the cosine sign. So that says we still have oscillations. It's still going up and down. The e to the minus 2t in the front says that our oscillations are getting smaller. So it's oscillating, but over time, the signal is getting shorter. It's being damped, right? So that's underdamping. Means underdamping is there's a small bit of damping. So small, it doesn't kill the oscillation. Oscillations are still present. It just takes time for it to go small. Okay, on to our initial conditions. So, x of 0. X of 0, well, we plug that in. And e to the 0 is 1, and cosine of 0 is 1. So we're going to get c times 1 times 1. And then e to the 0 is 1. Sine of 0 is 0. So plus d times 1 times 0. So that simplifies to c, but we also know that x of 0 equals 2. So now we are like, aha, c equals 2. Nice. Okay, we need to do x prime of 0, which means we need to take a derivative. And here was, maybe this might be my last time I say this, another place where people were making mistakes. And if it was just 1 or 2, I'd be like, well, it's just 1 or 2. You guys, you comedians always coming up with these funny ways to take derivatives. It was not just 1 or 2. So let's talk about our derivatives here. When we're taking the derivative of e to the minus 2t cosine 5t, what rule do we need to take the derivative of this product? It's the product rule. That's right. Good job. You nailed it on the first guess. So, what is x prime of t? Well, okay, so I have the c. And I'm just going to put parenthesis here. Take the derivative of the first. All right, the derivative of e to the minus 2t. Well, it's e to the minus 2t. Chain rule says the minus 2 comes down. So, minus 2 e to the minus 2t. The second function stays as is. Derivative of cosine is negative sine. So we'll have the first e to the minus 2t times the derivative of cosine, which is minus sine of 5t. And here's what was happening. Do I need anything else here? You'll notice I haven't closed my parentheses yet. I do. I need the 5 to the inside. Now, here's what was strange, which was making me scratch my head. People were getting the minus 2 because, their derivative of that minus 2t is minus 2. But the same idea that says, hey, if I take derivative of 5t, I need a 5, they weren't putting the 5 there. Which makes me go like, please, my students, I love you. Please do better for yourself. Okay, now take derivative of the other term. Well, it's very similar. So derivative of the first, minus 2e to the minus 2t, sine of 5t, and then the first alone, derivative of sine is cosine. So cosine 5t times 5. Okay. Now, that's x prime of t. We're going to take in x prime is 0, because x prime is 0 equals 1. So, x prime is 0. Let's do that. I'll switch colors again. So, we get that x prime is 0 is, well, we're going to get c times minus 2 times 1 times 1. So that's minus 2. And then 1, sine of 0 is 0. So that'll just be 0. So let's just say c times minus 2 plus d minus 2, e to 0 is 1, sine of 0, 0. So that goes away. E to 0 is 1, cosine 0 is 1, plus 5. So 1, 1, 5 makes 5. And that all equals x prime is 0, which we said is 1. Remember? 1. Now we know what c is. C is 2. So this is really minus 4. So we say, okay, if we add 4 to both sides, 5d equals 1 plus 4, which is 5, which tells us that d is 1. So we know what c is, we know what d is, we know what x of t looks like. So the final thing, since we're after the position function, is just to put it all together. So our position function is x of t is equal to 2 e to the minus 2t cosine of 5t plus e to the minus 2t sine of 5t. And that's it. We're all done. Because that was the last problem. That was number 6. We worked it out. We have a nice problem. And, okay. Well, we took our time. And you might say, well, that took about as long as we were given for the exam. Yeah, but we went slow. We talked about errors that people were making. We weren't rushing. And this is a little old here. It turns a little bit slower than you did. I don't think the problem was time on this exam. A lot of people finished early. Some people finished halfway through. Doesn't mean they necessarily had the best answers. But it wasn't time. And I think it was mostly just a matter of, are you being careful? Do you know what type of problems they are? And make sure that you don't do too much. There were so many people that tried to do too much. Even on this problem right here, number 6, there were a couple people who said, hey, do I need to rewrite this as like square root of 5, e to the minus 2t cosine 5t minus theta? And the answer is no, because the problem doesn't ask you to do that. Don't do things that the problem doesn't ask you to do, because that gets you into trouble. And there were other people who were like, hey, I memorized all these formulas. And one of the things I remember is that there's this nice little thing about how you can find, because you have like this cosine omega naught t, and omega naught you find by taking the square root of k over m. And people were like, okay, so that means we have a square root of 29t in our answer. But when does that apply? See, that applies if there wasn't any damping going on. So in other words, it looked like x double prime plus 29x. But there is damping going on. So that formula doesn't apply. So there's a danger of knowing a lot of formulas, but not knowing the context of when you use those formulas. Well, how do you get better at it? Well, for me, I try to minimize the number of formulas I memorize and instead focus on ideas. Do I understand the ideas? Do I understand the processes? Because those tend to be the things that are more helpful. It's more flexible for me. Because then I don't have to memorize 20 different variations of formulas. I say, well, look, there's 2 or 3 basic processes. And if I remember the processes, I can just get the parts I need as I go along. And so that's another suggestion. All right, well, thank you for being so patient, waiting so long. I hope you did okay. And I hope that this exam doesn't discourage you. You're bright people. We love our students. And I hope that you learn from this exam, pick yourself up, and keep going for the next one. All right, we'll see you again.